Hi, back again, and sorry for this just now. So then we go to the principle of effective stress. So the effective stress equations for continuum are looking from the six components as you can see here. So in the some mechanics, saturated soil is considered to be comprises of two gases, pore water and soil skeleton. We can consider the effective stress to be quantified, which characterize the contact forces between the soil grains in the soil skeleton. So in general, the higher the effective stresses, the higher the contact forces between soil particles and thus the higher is the friction resistance the soil particles have against relative sliding. So the friction resistance of the soil particles against sliding is characterized in turn by its strength. The higher the effective stress, the higher is the shear strength. Okay, the example is showing to you one element of soil subjected to the compression stress 100 kPa, 100 kPa compression normal stress, and the shear stress is equal to 0. You need to find resulting normal stress increments in vertical, lateral, and out of plane, and shear strain increment. So given that the vertical normal strain increment, delta strain y, delta strain gamma, and also shear stress increment, substitute to into these equations. So the Young modulus is a 10 MPa, the Poisson ratio is a 0.2. So you get the so this one E over 1 minus 2V is equal to so this one is E over 1 minus 2V plus 1 plus nu. So we have to substitute this equation. So we get the the value is 1388.89, and then you substitute accordingly to the equation stress increment in X, stress increment in Y, and stress increment in Z, while the shear modulus can be calculated here. Also, the shear stress increment is equal to 0.48%. So for your informations, these equations are given in the appendix. So for this class, I just show you how to apply the formula. Okay, we go to the next one on the topic shear strength. So shear strength is a common one, but the issue when we have a strength for case that the shear strength parameters effective Phi and effective C are not necessarily unique for a soil, but may depend on the strength history or the relative density in the case of a sand. Okay, in order that the Phi effective and C effective parameters obtained from the lab tests are similar to those that exist in the field, it is important that the lab tests are carried out on undisturbed soil samples which are subjected to initial soil pressure that are similar to those in the field. So it is important to take the sample with the minimum disturbance because we want to control the 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 contact of the sample which can get the undrained parameters. This example, as you understand in the previous class, I have shown you a difference in the analysis when you adopt the analysis by using the finite element method in the Platzi software. So in Platzi, there are four categories to adopt the technique with the method A, B, C, and D. So you have to discuss whether method A will suffer from similar problems in dream analysis. So please get back the notes and try to solve the problem. Okay, how we can define the shear strength? So basically, this is where we can define the shear stress of the soil. So if you have a series of consolidated untrained tests and obtain the following failure envelope, where the C is equal to 0, and one of the specimen that you tested failed at principal stresses, producing the mark circle shown. What would you report as the shear strength of the soil? So by plotting the Morse circle and the failure envelope or the failure line touch the Morse circle, we can have that the shear stress failure uh, or the failure strength tau ff is less than maximum shear stress tau max. The maximum shear stress tau max is obtained on the peak of the curve here. The above definition of shear strength is consistent with the Moore column model and is used in many computer programs to calculate if and when plastic yielding occurs for a soil element subject to the set of triaxial stresses. However, not very convenient when applied to the interpretation of results from triaxial tests. In triaxial tests, we can readily obtain final principal sigma 1 and also sigma 3 final from the measurements. However, unless we do a series of tests, we may not be obtain effective phi and also effective C. If we do not have effective phi and C, then we can obtain the point of tangency of the failure envelope with the Moore circle. For example, this case. So for the case of undrained and drained strength, so let's say you have plot the Moore circle for final sigma 3 and also final sigma 1. The peak of the Moore circle, you can say the maximum shear stress, also can be called undrained strength or drained strength. And then you take a straight line from the peak of the circle, you have the effective sigma 1 minus effective sigma 3 over 2, or this is similar to the radius of the circle. Hence, you will find that in practice, when most engineers interpret the value of shear strength from triaxial test, it is usually computed as this one. Sigma D or sigma U is equal half of deviator stress. They seldom define regardless as the shear stress at the point of tangency between the effective C and phi line and the Mohr circle. Okay, relationship between strength ST and the effective phi. So let's say we have this case, and then how the definitions or how this formula is derived. So looking to the Mohr circle here, we have the Mohr circle, and we also have the failure envelope which starts to the Mohr circle. Again, the point of the failure line and also to the Mohr circle here is referring to the shear strength at failure, while the peak of the Mohr circle is referring to the drain strength or the maximum shear stress. So the SG, the strength drain of the sample, is derived from the ST over effective C plus ST. Okay, looking to this one, sin phi sin is equal to ST here over to the sigma C plus ST. ST here is the radius of the circle. Up here is a ST, up here is also ST, and also up here is the ST. Thus, the drain strength is equal to effective C times sin phi over 1 minus sin phi. ST is a function of effective stress. So again, even though that we know this is the case most of the time when we have the sand where the C is equal to 0 and phi have the value, so we can derive the drain strength and the phi prime by by getting this formula from the Mohr circle and failure envelope. Okay, this is one exercise. Okay, you have to show that how the answer is a 212. And then next one, when you have the non-zero phi effective and C effective, how to derive the ST, the drain strength. So again, taking the sin phi, where is the sin phi? Sin phi is located here. Sin phi is equal to ST over ST plus sigma C plus C cot effective phi. So rearrange the equation so that you can have the drain strength. So this is where we can have. Okay, the next one, if you have the undrained strength SU and then the effective phi. Again, right now, for the case undrained strength, we have the total stress in the green circle, and also we have the effective stress in the red circle. You can see that how the total stress increase until reach to the failure envelope on the blue line here. So the Mohr circle at the failure is drain test carried out. So we have the SG. So for the undrained, we can have two parameters. Sorry, I mean that here we can get the undrained strength as U. So for cell with C equal to 0, and noting that AF is a pore pressure parameter is equal to UF over Q. And then the Q is equal to 2SU. So substitute the equation here. For example, sin phi is equal to, this is the sin phi, Sin phi here is equal to SU over sigma 3 plus SU. It is also equal to SU over sigma 3F minus UF plus SU and then when you rearrange the equations here, the final undrained strength is equal to sigma effective C times sin phi over 1 minus 1 minus 2AF sin phi. If you have the undrained strength with non-zero phi and C. So this is what you can have equations. So this one example, if you have a normal consolidated clay, C equal to 0, phi equal to 26, the A factor failure is 0.9. The sample A and B are consolidated to an effective separation of 100 kPa. Sample A is under drain condition and sample B is under undrained conditions. At what divided stress will each of the two samples fail? So we go to the sample A. Since the sample A is failed under drain conditions, so we can say that this effective C is equal to 0. Substitute the formula, so we can get the ST is equal to 78.1 kPa. Because the question asks what is the deviator stress at failure. So what is the deviator stress? Deviator stress is the difference between the final sigma 1 minus final sigma 3. So the ST is equal to the radius of this circle. So we have to add another ST so that you can get the deviator stress. That's why here the deviator stress for sample A is a 2 times of the ST. So the final answer is 156 kPa. So similarly, for the sample B fail in the undrained conditions, so that we notify that C effective equal to 0, and then we substitute into this respective formula. What we can have the final one, the deviator stress Q is equal to 65 kPa. Yeah, so you can see that in the undrained conditions, the deviator stress Q is lesser than in the drain conditions. So we go to the stress path. So the stress path is convenient to represent the state of the stress by the stress point. So which has the coordinate sigma 1 minus sigma 3 over 2 and sigma 1 plus sigma 3 over 2. So you have to use the coordinate T and S. So it's a T on the y-axis and S on the x-axis. However, the T and S will be changed in the respective formula. So again, how the T and S is plotted. So on the left graph here, this is the case where we have a few circles or more, and then from the sample A, from sample B, and from sample C and D. What is the point A, B, C, and D? Point A, B, C, and D is the maximum of the stress point. So the D is equal to the tau max. So the tau max is equal to sigma 1 minus sigma 3 over 2. So this is also similar to the radius of the circle. In order to represent all the circles in one line, so it is transform all the stress point A, B, C, D into a straight line here with an appropriate tangent with the angle 45 degree. So this is the example how a successive mole circles is transformed to the stress path B. Okay, this is the conditions common stress path for different cases. Okay, for consolidated untrained characterization test, it is very important for you to understand the situations where the sample is under consolidations and when the sample is under sharing. So what will happen due to in the under during the consolidation, the samples is fully trained.